what I simply mean is it dictates the off time for the flashing light, okay? For the flashing light. And then this, again, the same thing for the on time, so that it dictates how long is the light off and how long is it on. So that again makes the flashing sequence, which is adjustable. You can change how long it stays off and how long it stays on. Okay. This is not the only application of this flasher logic circuit. It's used in several other reasons. I think I mentioned in your notes, for those of you who probably have gone through this, that another way is if you're using it in a paper shredder or even a plastic shredder. You can always see that if you have a shredder, you can dictate how long it runs forward and then how long it runs backwards or it reverses. So because of that, running forward and backwards, you can use these two timers together. One to dictate the forward run, and then another one to dictate the reverse run. So it's basically when you want to use an application that requires some cyclic sequence. There is a sequence either up and then down, or forward and then backwards, and then it repeats. So if you need something that requires a cyclic sequence, then you can make use of these timers. So it's not basically just for flashing lights and on and off, but it can also be used for other cyclic applications or cyclic sequences. That's very, very important to note. Okay. So now we quickly want to see how we can introduce this kind of sequence in our circuit. Now, you can imagine that when we have been building our ladder diagram, it keeps growing. So it means that, sorry, it looks very untidy, but it's because of the different explanations I've been giving before. But my point basically is, if we want to try and improve on this ladder diagram, you can see that it keeps growing. It becomes bigger and bigger. So basically what we want to do now is introduce a section. So it means that we are supposed to draw the ladder diagram from the beginning, from rung 1. But because of space, I will not do that. I will only draw the section that works for us today, or that makes use of the principles that we are learning today, so that I don't have to redraw the entire diagram. But for you, you'd be expected to redraw the entire diagram, meaning you have to take care of the whole ladder diagram from rung 1, such that whatever you draw now would be a continuation in this. So you continue again drawing like that. So it becomes a longer ladder diagram. Okay. So I'm only segmenting it for this case and because of just limited space reasons. So typically, again, because we want to introduce, so let me just indicate example. Okay. And so that I provide an instruction that makes sense to everyone. So let me just say, using the motor control ladder diagram example, in bracket already discussed, we can add a flashing warning light. Now, the instructions here are very important. Don't always assume what you already know. Try and read to understand. This flasher circuit is supposed to operate, or is supposed to be activated after the motor starts running. So remember the sequence initially. So let me just indicate here that the flasher logic will activate after, sorry, will activate after the siren has sounded. Let me just say has sounded, and the motor starts running. Because if you remember what we did, we built a latching circuit. Then after latching, we went to the siren. And then after siren, now we want, of course, after siren, the motor is running, because the motor was supposed to run after the siren has sounded for a particular period of time. I don't remember how many seconds. I don't know whether it was 10 or 5. But after the siren has sounded, the motor runs. Now, after the motor starts running, we need to have the flasher logic or the flashing warning light. Let me just indicate the flashing warning light. The flashing, let me just indicate that the flasher light. Okay, so that's basically, so we have covered this. We covered this, and of course, I mean, this is already basically the main thing. So this is what we need to introduce in our circuit. So typically, we also just have to figure out what more outputs or inputs do we need to include. Now, if you remember, this, the output to this, the output that we had here was, I think it was the M1. Let me just check. It was the M1 run, yes. So M1 run was the output. Okay. So it means our M1 run output now needs to become the input to the flasher circuit. So I can indicate that here, that M1 run output, let me just indicate in the previous run. In the previous run, because now we're going to continue drawing it, is used as the output, is used, the M1 run output is used as the input, or what we call the trigger, to our timing circuit. Because a flashing circuit is all about timing. Remember, you want the light to be on for a period of time, and then it goes off for a period of time, then it comes back on for a period of time, and then goes back off for a period of time, and that continues. And that is what a flashing circuit basically is. So it's a circuit that basically delays the time that a light is on and a time that a light is off, and then that repeats itself. It's a cyclic process. So let's check again. What are the inputs that we need? Because our circuit is the original circuit, we still have the M1 start, for those who can remember. That remains the same. We still have the M1 stop. That remains the same, because the start push button, the stop push button, and we also had the M1 the overload. So you can see here that there is no change. No change with previous example. Okay, our circuit still needs the same start button, the same stop push button, the same thermal overload circuitry. So that doesn't change. What we need to understand is, because we need a flasher circuit, so we need a light that flashes, and the light is a physical device because we need to see it, and therefore it becomes an output. So the outputs, we need to add outputs. So let's check outputs. The previous case, if I can remember, the M1 run was an output, which is for the motor to run. Okay, I think we had M1 siren because we had to hear the siren blare. So those were the outputs. We had the motor running, an output for the motor to run. meaning we needed a device that we connect to the motor for it to start running. We also needed a device that we connect to the siren so that we can hear it blare. And so the other output that we now need, we can call it M1 light, because now this is a flasher circuit. So if we were labeling this, I think it was output 1.0 something, 1.0, then this becomes output 1.1, then now we have an output 1.2, something like that. Okay. Of course, these are all normally open contacts because they are like this. They were all like this. They're just normally open contacts. So this is a normally open. This is normally open. That's normally open. Not contact, sorry. These are outputs. So we call them coils. I beg your pardon. We call them coils because outputs are coils, not contacts. So what we have introduced here for this flasher circuit is basically that guy there. Okay. So this is the new person introduced there. A system for us to see or the lights to go on and off. Then we had the internal variables. We remember the internal variables are not physical devices that we connect, but they are logic addresses or memory locations that help us command our systems within the ladder diagram. So we had the internal variables. I think we covered, I think it was just one in the previous class. So internal variables. So we had the start command. The start command was an internal variable committed to the memory of the PLC. So we had given it M1.0 because it was the command that therefore after the siren has blared, then now it gives the command for the motor to start running. Okay. And then, so now we also need a similar command that now tells the light to work after a condition has been met. So we can call it the light timer. So you need a light timer. So we can call it M1.1, something like that. I told you the addressing is as long as it's sequential because it depends on different manufacturers. I just need to see that there's a pattern or there's you're using a certain notation to address or to provide addresses for these commands or for these contacts and coils. But I will not penalize you on what type that you use. So if somebody uses Q, I don't know, depending on which one you want to use, but you better stick to one so that you're used to it every time. Now, remember the internal variables, these are just commands that help us activate the downstream equipment. The start command activates the motor to start running. Immediately the siren has stopped. And then the light timer is now, because after the timing delay has been achieved, because the timer is simply to provide the delay, once the delay has been achieved as required, then the light timer needs to now activate or tell the light to now either turn on or turn off. Okay, that's why those internal variables are important. And of course, I forgot the key things that we're using here are now the timers. Okay, so I don't know which timer. The timer that we had previously, we just called it timer T1. Okay, we had a timer T1. But now, because we have a flasher circuit, so this one was for, the first timer was for let me say, start delay timer that we used in the previous circuit. Here it is, the start delay timer. Yeah, we called it T1. Okay, the one that was delaying the operation of the motor. Okay, so now that was there. So we need to add two more timers. One to control the off, the period of time when the light is off, and then another one for the period of time when the light is on. So now, and remember, they are both on delay timers, only that they are operating in a different sequence. One delays the time the light is on, the other one delays the time the light is off. Okay, so we'll need T2 and T3. So you can have, let me just say, flasher off, timer, and then we have a flasher on, timer. Okay. So now that we have identified all the inputs, outputs, the internal variables, and of course, all the other elements, in this case, the timers, we now need to draw or continue with our ladder diagram. So like I said, we're supposed to draw this ladder diagram from scratch. That is from the latching circuit in rang 1. This was rang 1. Then we went to the siren in rang 2, rang 3 with the motor, and of course its timer. And then now we need rang 4 going onwards. Okay. So I will not draw all of them. It's just a continuation. I will continue from the rang 4. Okay. So I'll continue from rang, I think it's rang 4. Let me check. The previous circuit had already, yes, the latching, siren, and timer. So the flasher comes at rang 4. Rang 4. Okay. So basically, again, we have to understand, before we draw the ladder diagram, apart from the rules, we have to understand exactly the sequence of operation, and we make sure that as we draw our ladder diagram, we take into consideration that sequence of operation. It helps us to also interpret and quickly understand what is happening. We have just said here in the beginning that we are going to use our M1, did I indicate it? We are going to use our M1 run output. Yes, the M1 run output is going to be the trigger to the flasher timing circuit. So that means M1 run output is now being used as an input. It's the one that's going to determine whether when the timers start operating or not. And when I say the timers, I mean T2 and T3, because T1 is already in operation. Remember, we said that the previous ladder diagram is already in operation. So everything there is working. So we have the latching already working. We have the siren that is already in operation. And we have the motor that is already running. Okay. So the motor is already running. That is what we indicated here, that the flasher logic will activate after the siren has sounded and the motor starts running. So that's why we are simply continuing with the design. So we'll need an operation where the M1 run is what becomes our input. So M1 run, I don't know what the address is. I think it's I something. But now, because this was an output, it's going to be output. M1 run was output something. Output 0, 1.0. Output 1.0. Okay? So this is what determines what happens. Remember, we want to use two different timers. One to control the time the light is off, and the other one to control the time the light is on. So one is the light off timer, the other one is a light on timer. Now, usually, because when you connect your circuit, you don't connect it when the light is already on. So we'll use T2 to be the light off, because that's the first state of your flashing light, because it comes when it's off. So you expect that off position to remain for a period of time before it then turns on, and then it will repeat. Okay, it would alternate. So now, again, you don't always have all the full information when you're drawing the ladder diagram, but you try and do everything that is required in each rung. But if you have not made, if you look at the sequence of operation and you see something is missing, you can always adjust. So I don't expect that when you are designing, you already know everything to put in each rung without having to come back and readjust. So you just have to use common sense or logic in this case. And then as you draw the components of each rung, you might miss out on a certain condition or a certain requirement. But when you move on to the next rung, you realize that you need to incorporate it in the previous rung. So you can always come back and readjust. So that's exactly what I'm going to do. So we just have a case where we are introducing the previous output to become the input. So for example, we indicated that in the previous output that the motor is already, the siren had sounded, and now the motor is already running. So then when the motor is running, I expect to delay. So I'll use a timer. I'll put a timer like that. If there are any adjustments, I'll make them later. So T2 is to control the duration in which the light stays off. So we use our on delay timer. I think we were calling it TON, but we're actually writing it on timer delay or on delay timer, no problem. On delay timer, as long as we know there's the point where there's a start, there's the preset, there's also the done bit, okay? Now, so again, depending on what the instruction is, this preset time can be either, it can be 2 seconds, 3 seconds, 1 second, 5 seconds, depending on, but you see for a flasher light, it shouldn't remain off for a long period of time. So let's use the one that's in your notes, I think is 1 second. Okay, so 1 second it's off, the other second it's on, so that you can actually see the quick flashing. So then, of course, we connect it to our output, which is the light. Okay, we had our output there as M1 light. Okay, M1 light. Okay, output 1.2, something like that. Output 1.2. So that's, so basically, again, you can always just see when the motor starts running, I expect this to be logic 1. So that's true. Logic true means that the timer starts doing its work, counting. So the timer counts, then 1 second later, the done bit comes to logic 1. Actually, remember, I told you that it's the done bit that's connected to, so that it makes it clear, it's a done bit that's connected to the output. So that when the done bit, because it means the timer is done counting the time. So once the done bit is logic 1, then we expect now the light to go on. Okay, so it has been delayed. It has been made to stay off for a period of time, but then once that period of time has elapsed, then it goes on. Now we need to find a way of taking the light back off. So you can imagine if, for example, so we'll readjust this. I'm just saying, if this was holding true, then of course the timer is activated. And once the timer has been activated, then you have a logic high here. So this is true. And of course, the light goes on. But because we are using 2 timers, one to control the time it was staying off, the other one needs to control the time it takes before, it turns on. It stays on, not turns on. The time it takes to stay on. Because now remember, the first timer, T2, has delayed the time that the light goes off, because it's just one flasher light. It goes on and off. But now we want one that will delay the time it stays on. So it means, therefore, we'll have to introduce, and that is controlled because it's this output now becomes the input, because once this is true, then the light goes on. So we need to ensure that from that point, we use that logic to control the next timer. The output of one timer controls the input of the other timer. of the next timer. So now we'll have this as our M1 light, the output 1.2. But now we need to connect it to the start of our other timer, T3. So we connect it to the start of our other timer. And of course, we also have a preset value here. Could be a few seconds or just 1 second. And of course, you have your done bit, which is now connected to the. So this we can call, this is now, because this is the one that's in the memory. So we can call it we called it what? The light timer. Let's call it M1 light timer because it's for motor 1. So M1 light timer. Okay, it's the memory one. 1 point. It's memory 1.1. Memory 1.1. So actually, now what happens is this is now what we connect to a flasher light, okay? Where there's the off time and the on time. So it's mounted somewhere, okay? So now, again, maybe some period here, I don't know, 1 second, okay? So now what happens, because let's see if this makes sense, and if not, then we make adjustments. So during the scan of the 4th rung, we can see we have M1 is true, M1 run is true, meaning the motor is running. When the motor is running, M1 run is true, okay? So therefore, it means logic is flowing. And what does the logic flow to? It flows to the timer. So the timer is activated. And so when the timer is activated, it provides the delay necessary based on the preset time. The delay here is 1 second, okay? And so once that delay has been achieved, the done bit goes to logic high or logic true as well, okay? So once the done bit has gone to logic true, then it means that this M1 light output is also true, okay? Now, let's go back. Once it's true, then of course this is also true because it's the same memory location. And therefore, when it's true, then T3, of course, is activated as well. And then it delays the timer. I mean, it delays the period in which the output is achieved. So by about 1 second in this case, and then the M1 light timer goes on. Now, there's something missing from this already that I can see. We expect, and this is why it's good to draw, and as you draw, you try and absorb what is happening. And then if there are conditions that are not yet met, you include them, okay? We expect ordinarily that this, when the timer T3 is working, T2 is not working. Because you cannot have T2 and T3 working at the same time. If they are working or timing at the same time, then the sequence is going to be mixed up. We expect delay to be provided, then the light goes on, and then the delay to be provided by time T3 for the light to then go back off. So therefore, it means I need to take this output here. I need to bring it as an input to this timer so that when the condition of this is logic 1, for example, I expect that the timer T2 is deactivated. And when the condition for this is logic 1, of course, this timer, the output here will also not be working. So that you are either at one point controlling the time the light is on, and then another point controlling the time the light is off. But you can't have them running at at the same time. That will not make sense. So therefore, it's easy to adjust that. And you know by now that to adjust that, all I need to do is introduce a normally closed contact here. But the memory is assigned as M1 1.1. Okay? So this is the M1 light timer. This was the light timer. Light timer. The reason why I've introduced it as a normally closed contact is this. It's such that, let's say timer T3 is doing the delay and then it transfers a logic 1 at the output, or a logic true. So when it provides a logic true here, we know very well that a logic true on a normally closed contact gives us, remember truth table. A normally closed contact, you either have the input and output here, like that. If this is true, let me just start with false because it's 0, 1. So let me start with false. So if you have false here, if I have false, I expect, this is for a normally closed contact, okay? False, I expect true because it's a NOT gate. And then when we have a true here, I expect false. So now notice, if timer T3 is working, then the output M1 light timer will be true. And so if I use a normally closed contact, that the output would be false. Okay? If the input that now, because now remember, this output is now used here as an input. And if for a normally closed contact input, if it is true, then what it is giving you is false because it's a NOT gate. So therefore, if this state here is true, then it's blocking logic. That's why we are saying it's a false state at the output. So because it is true, we know that the logic that is being passed is 0. So T2 cannot work. And if it is false, then the logic provided here is true. It's a logic 1. And therefore, this guy is working. But for it to be false, it means that this was false. And if this was false, it means that the timer is not operational. So that way, timer T2 works when timer T3 is off. And timer T3 also works when timer T2 is off. So those adjustments might not be seen initially when you are drawing your ladder diagram, but when you're looking at the sequence of operation, you can quickly spot them and readjust them accordingly. So that's why I usually recommend that when you're doing your exams, you use maybe a pencil when you're still drawing these ladder diagrams before you draw a fair copy, because otherwise it would mean you're rubbing off. And now when you start crossing it using ink, then it will not make sense. So let's revisit this and then we close this chapter because I want to look at today's example. So let's look at how it works now. So let's see, the motor has started running in rank 3 based on the conditions that have been provided. We are just following the sequence, the scan cycle. So we have a logic true here. Let's see if it will make sense now. Remember, there is nothing here. So let's say this at this state, it is false because there's nothing. The timer T3 is not working yet. It's just been connected. It's not running, so it's false at that state. So if it's false, the condition here is false. Remember, being a normally closed contact, if you provide a false input, then it means you're having a logic 1. It's passing logic. False input equals to a true output based on the truth table. So you already have a true here. Output, the false input. Remember, this is input, not output. It's a false input. That's what we are providing through this. So the output is true. So you have true, and so motor T2 is activated. When motor T2 is activated, then we're expecting here to be true. Okay? Now, because we have the M1 light is now allowing logic. Okay. So we have true in that output. So once it becomes true, that is timer T2, after 1 second, will trigger the output and the output goes to true. So then you'll have the logic that is flowing through M1 light output, and it also goes to true. So if you have this true here, then of course this one becomes true because it's the same address. Okay. Now that we have true here, because it's picked from this address, in our second rung in this case, but actually in real sense it is now rung 5. Okay. So now that we have true here, what that basically means, therefore, is we expect T3 to be activated. Now, when T3 is activated, please follow the sequence keenly. While we have T3 being activated, then of course it starts timing. Then after the delay, it provides a logic 1 on the, or a logic true on the done bit. So this would be a logic true. As soon as this is a logic true, this guy is updated as a logic true. This one is updated as a logic true, meaning the input is true, so the output would be false, and so this guy will have to be deactivated. So now notice that now this is true, so we have moved from false where it was previously, now it is true, and so the light, the flasher light starts working. Okay, so while timer T3 is timing, while it is timing, it's providing a logic 1 at the M1 light timer, or a logic true, and by doing that, it deactivates T2. Okay? So therefore, depending on the preset time, that will control the time the light goes on and off. Because now look at it. If this is true, that is, if we have a true here, then the light, remember, now goes on again. And as soon as it goes on, this was true. I told you then, therefore, that timer T3 is off. And if timer T3 is off, then this here should now be false. This now goes false. And as soon as it goes false, you know that this one, of course, the same memory location. So this is also false. And as soon as that becomes false, of course, the timer T3 is deactivated. When the timer T3 is deactivated, the light goes off again. Okay? But because the output here would be false, this becomes false, and then this becomes true. The output becomes true, and then timer T2 now goes on again. So it keeps cycling like that. Okay? And the cycling is just based on the way these timers are connected. When one is operating, the other one is not operating. And therefore, through that, we can control the on-off time. So remember, the preset times can change. You don't have to put them as 1 second each. Maybe the first one can be 1 second, the second one can be 2 seconds, depending on how you want your flasher light to remain on and also to remain off. Okay, but the key thing is to note that T2 and T3 are operating sequentially, but not at the same time. Because one, it's like T3 resets T2, and T2 resets T3, and vice versa. So they keep changing each other. Okay, so when the light is off for T1, it's on for T2. And then it keeps changing like that. So that timing sequence, remember, this is connected to the motor circuit. And this part of run 3, yes?
Sorry for interruption. Eric Ogura got his hand up. Maybe he got a concern.
Oh, there's a hand up? Please, I'm not able to see your charts yet. So if you put your hand up, I'll not be able to see because I'm in presentation mode. So just feel free to interrupt and ask. So somebody, if you want to ask, just go ahead and ask.
Yeah, I just wanted to ask that from the description you showed that T2 is a flasher off timer, but in the diagram you've indicated there's a timer on, it's a timer on timer. So like somehow creating some sort of confusion.
Just ask again. You're saying that T2 indicated is a flasher off timer.
Yeah. Okay. It is flasher on. I thought it was timer on.
Please note the description that I've provided here is not timer on or timer off. I've provided as flasher off and flasher on. So both these are on delay timers. It's on delay. This is also on delay. So the thing is, this first on delay controls the time the flasher is off, and this on delay controls the time the time the flasher is on. So it's basically saying that the first on delay delays the off position of the flasher light, and the second on delay delays the time the flasher light is on. So these are on delay timers. Even this one is an on delay timer. None is an off delay timer here. So is that okay?
Thank you.
All right. Sawa.
Excuse me, sir.
Okay, go ahead.
Excuse me, sir.
Yes.
So, how long does the M1 light timer stay on? The M1 lighter. The
M1 light
timer.
timer. Oh,
yes, how
okay.
long does
So
it stay?
Now, the time it stays on depends on the preset value that is provided. Okay? So if you look at this carefully, you will see that the preset, the timer, like for let me just put it clearly, that the time this takes to stay on depends on the preset value that's provided here. So for example, if we provide a preset value of 1 second, so it means this flasher will stay off for 1 second, and it will go on for another 1 second. Okay? And if you change it, then we'll now maybe make this 2 seconds, then it will be off for 2 seconds and on for 1 second. So it will still be flashing, but on different time levels or time intervals. And so the M1 light timer is basically the time or the duration is controlled by the preset value of the timers. So the longer the preset value, the longer the light timer stays on and off. Because remember, this M1 light timer goes on and off depending on which timer is operating. Because I told you T2 is presetting T3 and T3 presets T2, but the preset value is already provided there. In this case, for uniformity, we've given them 1 second. So the M1 light timer is supposed to stay off for 1 second and on for 1 second. But you can change, you can play around with that. Okay? And I would wish that for you to have this, and I was really hoping that by now you guys have installed. It doesn't have to be Cymatic S7. You can install any other PLC software and just simulate these things and see how they work. You'll get to really appreciate, because when you simulate them, you can play around with the preset values, see what happens. You can play around with the contacts, change them to normally open, see what happens. Then you get to appreciate. I think I will look for a session. It's only that, it's very difficult, guys, to get a projector and then run these simulations live and then you see it. So maybe what I can do is I have a software where I can like simulate a demo and then play it as a video, so you can actually see based on the demo that has been pre-recorded. That probably can help those students who cannot do simulations by themselves. But for those of you who are objective enough and have access to these softwares, because we have already drawn the ladder diagram, all you're going to do is drag and drop them accordingly, then connect them to the devices, in this case, the flasher circuit and the siren, then actually see what happens. Now, you might not have a physical siren, but you can use a lamp to indicate a siren, and maybe you put a red. So when the light goes, turns red, then that maybe denotes a siren. But then the flasher circuit, of course, you will see it flashing in different durations based on the preset value. So the time the light timer takes is based on the preset values of the timers. Sawa.
Okay, and what for, let's say like for M1 light, not for the M1 light, when it goes off, when the logic stands to false,
Yes.
will it affect the T3?
Now let's look at it. So let's say for whatever reason we are already here and this state is false. Sawa. So if this state is false, it's the same memory location as this guy here. Only that he was an output at this point. At this point, it is an input. So its state is the same. So the state here is also false because it's the same memory location. So when this goes off, remember this is just an output. We listed it as an output. Okay. So M1 light is false. Then this becomes false. And when this is false, it means it deactivates it deactivates T3, because if it's a logic false, it cannot start T3. So T3 cannot start. And because T3 cannot start, then the output here is false. But because the output here is false, notice we have it here as false. But here it is an input. The output here is false. But remember, this is an input device. So if you provide a false input to a normally closed contact, the output is true. So if the output is true, what happens to the T2? It starts. And so it delays the time, and then after 1 second, then it turns this output to true. Okay, so you can see, and as soon as this turns to true, then this guy becomes true because it's the same memory location. When it becomes true, then it starts T3. And if T3 starts 1 second later, you have a true output. As soon as this becomes true, then this is also true. And so we get an output of false, which turns off or deactivates T2. Do you see the sequence?
Yes, I see it.
Good.
But okay, okay, the last one. So for the preset value, it does not like matter on the previous logic. Let's say if it was set to 1 second, let's say for the T3, if it was set for 1 second, it will stay on for 1 second even if the T3 goes off.
Just say that. Just repeat the question again. You're saying that if T2 is, or if T3 is set at 1 second.
Yes, if the preset value is set at 1 second.
All right.
The light will stay on for 1 second without regarding like the previous logic. Even if T3 goes off, if it was set for 1 second, it will still stay on for 1 second.
Yes. Because this is an on delay timer, as long as it is active, it only delays the time the lighter, let's say now for T3, the light stays on. Okay. So even if the previous case, because as soon as you activate it, remember, as soon as you activate or you start the T3, it will start counting. The only reason why it will stop the count and change the state of the output is if power goes off, or if suddenly somebody shuts it down. And you can shut it down by providing a logic low or a logic false. Okay, then you can shut it down. But as soon as you're providing it with a logic high, it will delay that the time it takes for the lighter to go on by 1 second, even if the previous state is false. Okay, so it's like each of these rank 4 and 5. I don't want to say they're operating independently because they're not independent. One output is the input of the next. You can see that this output is this input. and this output is also connected to the input of the first one. So one output is the input of the next. So they're actually controlling each other. But remember, as soon as a timer starts counting, it's now active, and the state of the previous timer is now inactive, because when T3 is working, T2 is not working. So therefore, it doesn't matter the preset value of T2. The same way, if T2 is working, if you're having this as activated, T3 will not be working. So it doesn't matter its preset value at that point. What matters is the preset value of T2, because that is the only active timer. So these two timers, like I said, cannot be active at the same time. That's the nature of the connection that we have done, such that the two timers cannot be allowed to be active at the same time. Otherwise, it will be confusing. Setting the preset values can be very, very difficult. So that is what we have to remember, that it doesn't matter the state of the previous timer when one timer is working, okay? Because they are connected to work independently. When one is working, the other one is off, and vice versa. Any other questions, guys?
Excuse me, sir. Yes.
Go ahead.
I just wanted to ask if you can have, if it is possible to have a cascaded run, like having two outputs in the same run. And also I wanted to ask if you can use on delay time and off delay time, where we can use T2 to be on delay time and then T3 to be off delay time. So like,
all right.
Yeah.
Okay, good questions, guys. Now I'll have to confess that, you know, if I were to cover every aspect of every configuration for these timers, I will not be able to complete the syllabus. So I'm simply supposed to guide you guys, and then you do the rest. So yes, there are states where, and I think I'll give you a typical exam question and then solve it with you, where you can have cascaded outputs, such that you will need the output twice. For example, let me just say, let me wrap this off. There are cases where we can connect this output twice. So you can cascade the output. You know, this output here is provided twice. So while this is connected to a different device, this is also connected to a different device. Okay, we'll look at that. Don't worry. I think I'll give an example where this is used. Now, your next question is whether we can, a scenario where we can use an on delay timer and an off delay timer. So like T2 is an on delay, T3 is an off delay. Fine. So because we have 1 hour and I have another class in that 1 hour, let me do an example where we have a T2 as an on delay timer and a T3 as an off delay timer, not for this specific application, but for a different application. Is that okay?
Okay, thank you.
All right, so let's move on to that. So please, I think you can, this work that I'm already doing is I think I already provided you with this note. So you should probably now, when you read through, you understand better. But I highly encourage you to try and simulate this, because it's like using a circuit maker, where you simply connect the circuit as provided, then you observe how the output works. But because you've asked me to illustrate scenarios where you can use an on delay timer and an off delay timer, let us use one here. So let me give an example that can help. And I hope we can all follow through in the next 1 hour as we complete it. Please note this down, because we need to remember a lot of the instructions. Please, after you've spoken, just mute your microphone so that we are not interrupted. So the question is, consider the typical exam question. Consider a fluid pumping process that okay. Not say that. Let me just say shown. Fluid pumping process shown below. Okay, a very simple process. So you provided with 2 tanks. It's a typical application that you can see in real life. So we're given 2 tanks like that. So you have tank A, and then you have tank B. Then there is a pump that's connected between these 2 pumps. I mean, there's a pump connected here. Okay, so let's call this a pump. So because we have a pump, it simply means we want to pump water from one or whatever fluid it is from one tank to the other. In this case, from tank A to tank B. In fact, let me draw tank A as full. Let me assume tank A is full, like that. And tank B is empty. So we want to move the contents. So let me connect the pump. So let's say it's filled with water. So let's say the water is all the way up to that point. But this side is empty. Sorry. This side is empty. So there's nothing there. So that means because this is a pump, it's like a valve. If you open it, then all the water is released into tank B. So tank B will start filling up. Okay? Now, this is the direction of flow. Remember, this is because pumps come with one direction of flow. Some, I know it's 2 directional, but we're looking at the 1 directional. It's like a valve, like that, so that you expect tank A to fill tank B in this case. Now, usually, you can have pressure switches in between to be able to determine the pressure at any given point. So, for example, in this case, there are 3 pressure switches that are provided. Remember, this is a typical question. So you have a pressure switch here. Okay. Let me just indicate a pressure switch. So that's one pressure switch, PS1. PS1 is connected here. So let's have another pressure switch here. Like that. We can even have another one here. So we have 3. We have pressure switch 1, pressure switch 2, pressure switch 3, like that. So the question says that we consider a pumping process that is given here. Okay. So the question continues and says that the fluid is to be pumped from tank A to tank B. The operation of the process should be as follows. So this is what determines how you draw your ladder diagram, because they have dictated how it should operate. Okay, it's not left to you. Number 1, before starting, that is before starting the pump, PS1 must be closed. Remember, pressure switches 1, 2, and 3 are physical pressure switches. So somebody must manually close before starting the process. Okay? B, when the start button is pushed, the pump starts. So clearly, I know that there has to be a start button somewhere. So that tells me I need a start button, but we'll consider all those. But see, okay, the button, okay, let me even continue because it's part of it. It says that the button can be released. The button can be released and the pump continues to operate. The button can be released and the pump continues to operate. Now, if you've been in my class and you've been keen, that condition is called latching because you are pressing the start button, the pump starts to operate. Now, even when you release the start button, the pump needs to continue working, and that is what we refer to as latching. So therefore, I already know that in my ladder diagram, the first rung needs to have a latching circuit. And we know how to draw a latching circuit. I taught you how to do that. Now, part C, when the stop push button, when the stop button, let me just say, when the stop button is pushed, the pump stops. So again, if you've been in my class, you will figure out by now that a latching circuit is connected to the start button, meaning we have to branch out the output of the pump to the start button. And if we branch out, it only latches until a condition is met. And that condition is now stated here in part C, that when I press the start button, the pump will start to operate. Even when I release the start button, the pump continues to operate. The only way the pump will stop operating is when the stop button is pushed. So the stop button is the condition that gets the system out of the latch. That needs to make sense for people who have been in my class. Now, lastly, the other procedure that is indicated here is PS2, the second pressure switch, and PS3 must be closed. Must be closed 5 seconds after the pump starts. After the pump starts. If either PS2 or PS3 opens, if either of them opens, the pump will shut off. And will not the pump shuts off and will not be able to start again. Will not be able to start again for another 20 seconds. Okay? So these are the conditions that have been provided in your design. So maybe you have gone to the field out there, and being the engineer, you have been called upon, and somebody tells you, okay, we have 2 tanks here. We need to be emptying tank 1 into tank 2 or tank A into tank B, but these are the conditions that must be met. In our setup, we have 3 pressure switches, or actually just valves. One, they are connected as indicated in the diagram. One is on the pump itself, because you have to open the valve There's a valve on the pump itself. There's one that's connected to tank A, and there's another one that's connected to the tank inlet to tank B, the PS3. So the conditions that here is that before starting the pump, this is a condition. Before you start the pump, you have to close PS1. That's a condition. So somebody has to physically go and make sure that PS1 is closed. And then now they can go and press the start push button. And when they press the start push button, the pump will start running. Now, even if they release that button, the pump continues to run. It's only the stop push button that will make the pump stop. But now the gist of the story is in part D, or the gist of the design is in part D of these instructions. PS2 and PS3, that is the pressure switch on the pump itself, and also that's connected to tank B, must be closed 5 seconds after the pump starts. The pressure switch in PS2 and PS3 must be closed. So there's no way around it. 5 seconds. We expect that 5 seconds after the pump starts running, we expect that PS2 and, not or, and PS3 must be closed. So I am the technician on the ground. I ensure that PS1 is closed. Then I press the pump to start working. 5 seconds later, PS2 and PS3 must be closed. Now, if any one of them, if either PS2 or PS3 opens for whatever reason, then the pump automatically shuts off, and it will not turn back on until after another 20 seconds. So because these conditions, you can interpret that they all involve time. That's why we have 5 seconds, and that's why we have 20 seconds. So they all have time involved. But now, which timers do we use? So here you will see that one, PS2 and PS3 must be closed 5 seconds after the pump starts. So in just absorbing the question, you can see that we expect to have an on-delay timer to delay. So you will have a pump as an input, a pump somewhere as an input to a timer. So when the pump starts running, then it activates the timer. Just think about it, visualize it, because the instruction says, and I'm sticking to the last instruction, part D, that says when the when PS2 and PS3 must be closed 5 seconds after the pump starts. So therefore, the pump is already running. So the pump needs to be, it's of course an output somewhere, but it needs to be an input to a timer, so that we expect that once the pump is running, that's a logic high, it then starts a timer which needs to count 5 seconds. Then after those 5 seconds have elapsed, then we expect PS2 and PS3 to be closed. In case they are not, because it says if either PS2 or PS3 opens, then the pump shuts off. And once the pump shuts off, you don't expect, even if you press the start push button, it should not work up until another 15 seconds, or another 20 seconds have elapsed. So here you can see I'll need an on-delay timer to delay the time after the pump starts running. I'll need to delay for 5 seconds before PS2 and PS3 are closed. Then I'll need to check the condition of PS2 and PS3. If any one of them is open, if any one of them is not closed, then you expect the pump to go off, and it will stay off for 20 seconds. So this is where the off delay timer comes in. Because remember, the on delay timer is a timer that is used to delay a process for a period of time before it starts or before it's turned on. But the off delay timer is a timer that is used to delay a process for a period of time before it is turned on. Okay? So the on delay timer, the system is off. So on delay timer. So let's say a process is off. Okay? Then you use your on delay timer. So with a preset value, of course, once that preset value has elapsed, then the process is turned on. Okay? Now, in this case, our PS2 and PS3, remember, they were given here. PS2 and PS3 must be closed after 5 seconds. So PS2 and PS3 are open. In this case, we connect an on delay timer. So 5 seconds later, we expect PS2 and PS3 to be closed. Okay? Now, we need an off delay timer. Okay? For our off delay timer, this is how we'll use it. We have the pump is running. Then a condition for whatever reason has not been met. So we'll need an off delay. Okay, I didn't put something here. I just needed to indicate. Our pump was running. And then while the pump was running, we have here a condition not met. So if that condition is not met, what it translates to is pump off. We expect the pump to go off. And once the pump goes off, it is required that we have an off delay timer, meaning we delay the off position of the pump, off delay timer. We delay the off, in this case, 20 seconds, until a condition is met. So, condition met, not even until a condition is met. Once the delay period has elapsed, once the delay period has elapsed, then the pump can now, pump is turned on. Okay? So, the off delay timer delays the period the pump stays off. The on delay timer will simply change the condition of PS2 and PS3 after an interval of time. So PS2 and PS3 are in the open position, but we expect a countdown. So 5 seconds later, we need to close them. But the off delay timer, our pump was running, a condition was not met, so the pump switched off. We expect that off position to remain for about 20 seconds before the pump is allowed to turn back on. So that's where we're using the off delay timer. So let's now start trying to draw this so that we see if we can come up with the required ladder diagram in the next few minutes. We have 30 minutes, we can do it in 15. So inputs, again, quickly, because of time, I might not go into the addresses and all that. Now you guys know how to do that. I'm just trying to make you understand. Now, of course, the same culprits will expect a start push button, okay? Okay, we'll expect, and the start push button is already its condition. So the PLC wiring for this, so that you also don't get confused. The PLC wiring for the start push button, for those who now know, is normally open. Then we have the stop push button. That's another input that we'll need. And it's in the normally closed position. Okay? So the way we wire it, the device, the software itself would be put in the normally open, but we know that the PLC, the switch itself, is connected in the normally closed position. Then the other input we have is pressure switch 1, pressure switch 2, and pressure switch 3, because those ones have been mentioned explicitly in the conditions that are provided. Now, all of them should be in the normally open positions. Okay? All of them are connected in the normally open position. What I mean is, if I was to connect the start push button, then of course it's connected like this. So that when you press it, it closes. But for the stop push button, it's connected like this. It's already closed. Okay? So if it's pressed, it opens. That's what so this is start, this is stop. So it's this for the stop push button, it's already making contact. It's normally closed. So when it's pressed, it breaks the contact. But for the start button, you can see it's open. So when pressed, it closes, and therefore it makes the contact. And so the other PS1, PS2, and PS3 are the same switches as the start button. Okay, I drew them here. They were even drawn on the circuit. You can see they are open. Okay, now let's continue. So those are the inputs that we need. All right, then outputs. Outputs. Of course, there's only one output here. We are pumping the fluid from tank A to tank B. So the output itself is the pump motor. Okay, so it's the pump, because the pump is simply a motor. Okay, so that's your output. Again, you can give it an address. So these guys, you can say, I don't know, input 1.0, input 1.1, input 1.2, input 1.3, input 1.4. I don't have time for all this. Output 1.0, something like that. Okay, that's the output. But of course, we need timers. So we need T1 and T2. T1 is the on delay timer. T2 is the off delay timer. The on delay timer, will use it when the pump is running to delay. Once the pump starts running, we need 5 seconds delay before the pressure switches 2 and 3 are closed. Okay? We need the off delay timer such that when the pump is off, we need it to remain off for 20 seconds before it can turn back on. That's why we need the off delay timer. So we are delaying the off position of the pump for 20 seconds. Okay? And we are delaying the time the pump is on for 5 seconds. Then pressure switch 2 and 3 are closed. All right. Let's now see, because I don't think there's any other element here that we need to include. Again, if you have a comment, please just interrupt, because I'm not able to see your hands. But let's see now if we can come up with a diagram that makes sense. And again, like I told you, we are drawing a ladder diagram step by step using the logic, ladder logic. So in certain cases where we miss out the instructions, we might find them later as we move on to the next rung and adjust accordingly. So let's see. The one that everybody needs to get right is the rails. Just draw the 2 rails. But before we do that, let me make this easy. It means there's the part where the ladder diagram begins here. There's the part where the ladder diagram begins here. But then there's the part of the inputs, the input field devices, where number one, you have the start push button like that, connected like that. So this is your start. It will be connected. Then, of course, you've got your stop push button, which again is already making contact like that. So this is stop push button. Okay. Then, of course, you've got your pressure switches. Okay. They are in the open position. Okay. And there are 3 of them. So you can have them like now, this is PS1, PS1, then we can connect PS2. Okay. Like that. And then we can have our last one, which is PS3. Okay. Now you can see that PS1, PS2, PS3, the start and the stop push button are actual physical devices. So these devices needs to be operated manually. So somebody has to press the start push button, somebody has to press the stop push button, somebody has to close the pressure switch 1, close pressure switch 2, close pressure switch 3, and so on and so forth. But now the ladder diagram is what exists between the rails. And at some point, we'll need a pump, so you'll have a pump somewhere, and that pump is a device, a physical device. You know, there's a motor somewhere that needs to run. Okay, so this would be output field device. So those are hardwares. But what falls in between the rails are the softwares. So the PLC wiring that we are referring to here are the wirings that are done here. So you can see the start button is wired in a normally open position. Stop button is wired in the normally closed position. And so these ones are called PLC wiring because we are wiring field devices to the PLC software. So they are PLC wirings. Everything here is a PLC, okay? The devices are physical, but we have to wire them. Just like even traffic lights, you could see that, yes, you had your software ladder diagram written nicely, but you had actually to wire them to some lights, which are physical connections that you have to make. So those are the PLC wirings. Okay, good. So now let's see how we can come up with the ladder diagram. Now, the instructions were very clear. These ones we should do very fast now. Once everything is in order, it says before starting the pump, PS1 must be closed. So in your head, we should think, or in our minds, it should be clear that PS1 is a condition for the pump to do what? To start. So PS1 must appear in the first rung because it is a condition. Before starting the pump, PS1 must be closed. So it is a condition that must be met. Part B, when the start button is pushed, the pump starts. So the start button is also a condition in our first rung. So here we are identifying what we need to put in the first rung. PS1 needs to be there, and it's a condition to be met. We'll see whether we'll meet it. The start button is also a condition. It needs to be pushed for the motor to start. Then it says the button can be released and the pump continues to operate. So this is the latching condition that even when we release it, and I told you that a latching circuit is very simple. You take the state of the output, you make it an input, and you branch it out on the start button. Then you've achieved your latching circuit. So those two conditions are critical. And part C, the stop button is pushed, the pump stops. So the stop button must also appear in the first rung because the stop button is the condition that must be met for us to unlatch the pump. for us to come out of the state of the pump running, we need to use the stop button. So the stop button is used to unlatch the circuit. So A, B, and C is rang 1. Very clear. A, B, and C is rang 1. Because remember, if you go to part D, it says PS2 and PS3 must be closed 5 seconds after the pump starts. So it means we have met the output. Part D is after the pump starts. So let's first see how we can get the pump starting. That's what's important first. Let's see if the pump can start based on the conditions A, B, and C. Now, anyone who doesn't know how to draw a latching circuit at this point, all they need are maybe more prayers and revision. So we need a start button. The start button is a normally open contact like that. Okay? Now, because we want a latching circuit, we said that the start button is connected to a stop button. But the stop, let me draw it in green. Why? I'm drawing the stop button in green. It's an open, we said it's an open, a normally open contact. But, so this is start. And of course, the address is there. Then this is stop. So remember, the device here is already closed, but it is now connected to a normally open contact. But the normally open contact is active, because if I make it green, we said a normally open contact, if it is green, it is already passing logic, which is equivalent to the stop button. The stop button is already closed, so it is already allowing logic to pass through. That's why I've drawn the button, the normally open contact. I've put it in green, but it's for the stop push button. I hope that makes it clear. So it means this guy is already green. All right, it's already allowing logic to pass through. Now, the condition again, okay, go ahead. All right. Mm-hmm. 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 All right. Okay. I'll go back to this. I'll take my time here because I see there's still a confusion even from day one. Ladies and gentlemen, we have been presented here in our circuit with a device or a system to operate. Now, the question comes, we have declared that in the PLC wiring, the stop push button is always connected as a normally closed contact, which is very true. In fact, if you look at our wire diagram for the latching circuit, let me put it here. I will explain this until one day somebody gets it. If you remember, our latching circuit was connected like this. It was a start button and a stop button. And I think there was an overload or something was connected there. Then there's an output like that. And then this is for the motor. If you remember, for the motor where we were latching the motor, okay? So we had this guy here. So let me say this was A, this was B, this was C, and this is Y, and therefore this is Y, okay? So we say this is a latching circuit. So this is the start button, this is the stop button, this is the thermal overload. If it is provided, in our case, we are not given a thermal overload, but that's the thermal overload. And of course, this is the output for the motor, and you see the output for the motor is made as the input so that it latches, so that even if the start button is released, then the motor continues running up until somebody activates the stop button. That's when the motor will go off. So the gentleman has asked a very good question. Why is it that here in our latching circuit, we have a normally closed contact? But now here, lo and behold, I am drawing a normally open contact. Now, please, 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 I beseech you, understand me. I wish maybe, I don't want us to think in one dimension. It will confuse us. If you think about it, if I were not to include field devices, if these ones were not provided, because if these ones were not mentioned, you remember they have been mentioned in our setup. So if these ones were not mentioned, if I was not to include this part here, please note, if I was not to include that part here, then I am simply expected to do this, to draw this like that. Then I'll connect my output. Of course, there are other things that we need to connect, and then you connect your output. So this is a start button, this is a stop button, because it is the normal convention for a start-stop button. But ladies and gentlemen, there is a difference between just drawing a ladder diagram, meaning you are simply drawing whatever falls between this rail and this rail. That is it. But then when you are including wirings, and this will be more clear if you actually do this thing in a lab. If you are at home simulating, this environment, then I expect you to simply put a diagram that is the software part. You see, this is what you put in your schematic 7. Software. This is what you put in your schematic 7 or schematic. So this is the software part. So you'll put a normally open contact for a start button. Every time you want to use a stop button, you bring the normally closed contact and you put it there. Then you put your coil, and of course you do the latching and stuff like that. But if you are designing an entire system where you are actually expected to draw and connect the downstream and upstream devices, the input field devices and the output field devices, then you will notice, and again, that's why I say it is important if you try this physically in a lab. If you are connecting physical devices as well, aside from the software, like remember when we were doing traffic lights, we were designing the software at home, then you're coming up with your software, you come to the lab, you're given the lamps and you connect them, you're given whatever and you connect them. If we were to connect this, and then we decide to draw our ladder diagram like this, and then we decide to take a start button, put it there, then we put a stop button, so this is start, and this is stop, like that. Then, of course, the output like that, of course, and we latch. I'm not including the thermal overload here. It's not applicable in this case. So you have Y there and you Y there. If you connect your circuit like this, then you will see that your system is not working. The reason why it is not working is because the stop button that you'll be provided with is already in the normally closed, is already closed. So the entire system will be interpreted as this. Your entire system for the normally, the stop button, your PLC processor will understand the stop button as this. Something that's closed there and another one that's closed there. Now, ladies and gentlemen, even from logic, we say that if I give you A, and you double negate it, you simply end up with A. So you have not negated anything. So double negation is equivalent to no negation. Okay? So I'll repeat it. If you are in a lab setup and you are given input field devices and you have to come up with a software and connect them again to an output field device, The stop button that you're given, which is a physical device, already comes when it is closed like this. So then if you represent it again with a stop, a normally closed contact like this, then the PLC processor, if you operate the entire system, the logic will flow here it is negated, and again here it is negated. So if you had A here, you're still getting A there. Okay? And therefore, you will not have achieved a stop button. Because a stop means you want to negate what the input was. If it was running, you want it to stop. If it had stopped, you want it to run. It's negation. In this case, it was running and you want it to stop. So therefore, it means if it was running, I expect this and then it stops. Okay? So now, the only way to achieve that properly when you are combining the software part and the field devices part is to ensure that you have this. So that here it is normally closed, but here it is, so that it is like this. So that at the end of the day, the processor and the whole sequence, because these input devices form part of our connections, okay? So that now it will be understood as this. There's a normally closed, which is the actual button, but it's also connected to a normally open. So now you can see that here, if you're having A, you have an A that is negated there. And the value that you find here is based on whether you activate this guy or not. Okay? If you activate this guy, then you simply get that your A there. So you see you've negated. You've achieved the negation. That's why I was drawing this as green. I put the normally closed contact, but I draw this as green, meaning it is already activated. So you have A, you negate it as A complement, but then you activate this device so that it is transferred to the output as A complement. Because if this device is not activated, if this normally open contact is not activated, it is not green, then it means that it is not passing logic, because it's a normally open contact. So it has to be green. If it is green, then it is passing whatever logic it is given to the output. Okay? So now, I think we need to agree as a class. And I think I mentioned this in one of my classes. If you are asked to include the input field devices, then you'll have to draw for me the normally, you draw the stop push button as closed here. But when you're putting it in the software, you put it as a normally open contact, which is active. So it's a normally open contact, but it is green, okay? It is like that, because it's passing logic. It's like that. That is now your stop button. But in cases where the input field devices are not mentioned or we are not including them, we are simply talking about the ladder diagram itself without the field devices, then you can just draw this for the start and this for the stop and this for the output, okay? And then you can latch it, okay? So this is start, this is stop. Here, we are not making any references to input devices. We are actually just making use of the software on its own. So in the absence of input field devices, we draw our ladder diagram as this. But in the presence of input field devices, where they've been explicitly mentioned and their conditions also indicated, then if you were to include them, you see now here I have drawn them. So for example, this is how I will know the students who have been listening to me. I expect that if I give you a question and you decide that you want to draw the field devices, okay? So if I draw the field devices, I expect that I put the normally closed contact like this, but I leave this as open. Of course, it is activated, but it is normally open condition. But if I decide that I don't want to draw the field devices, then I expect you now to draw this. If I'm not drawing the field devices, then I'm drawing this. Like that. Are we together? So the reason why, ladies and gentlemen, I'm teaching you this setup is because if you go to the field and you're working with PLCs, you will not ignore the field devices. You will have to connect them. And I don't want you to go there and expose yourself and you say, you know, when we were being taught in class, we were told that the normally closed contact is connected like that, the normally open contact is connected like that, the coil is connected like that, and that's all I know. Whereas this is correct, it is not taking into consideration the input devices, the input field devices. If the input field devices are considered, then that means if you are to actually connect them to your PLC ladder diagram, then you will have to connect a normally closed contact, because the stop button is understood worldwide. Or everybody who manufactures a stop button in the world brings it when it is already in the closed position. And so when we are to make use of it in tandem with the PLC ladder diagram, what we have to do is to change this to a normally open contact, but we make it active. So that the logic that was here, let's say it is logic X, that logic X is passed here, okay? But because this guy is activated, so this guy negates logic X because it's a stop push button. So when it is activated, it becomes X bar. All right. So when you press the stop push button, it becomes X bar. So once it is X bar and we want to transfer it to the output, we have to use a normally open contact so that it becomes X bar. If we use a normally closed contact, it is still going to be X. And so you will have not negated anything. So I'll repeat this for the last time, and I have 10 minutes, so we might not complete this, but it doesn't matter. If you were to incorporate input field devices, it is understood naturally, internationally, and by engineers that stop push button comes as a normally closed contact. That's why we are calling the PLC wiring for a stop button is normally closed. So if you are to incorporate it into your PLC ladder diagram, then you use a normally open contact and you activate it. But if you were to ignore the input field devices, so you assume they don't exist in this case, you are only drawing the ladder diagram, the software part, then you are allowed to use a normally closed contact. So I don't know whether it is clear or I can repeat that again. Is it? Please take note. And even from the books that you read, for those who draw ladder diagrams without incorporating the input field devices and output field devices, we'll just use a stop button as this. But for those who incorporate field devices in the ladder diagram, so that you can see the field device connected, then you will see that they use a normally open contact, but it is in the active position, and that is what they connect to the stop button. Okay? So that simply means in practice, in the real world, if you are to use a stop button, then you have to activate the normally open contact that you use in your ladder diagram, because that is what exists in the real world. But in the abstract world, where we are simply explaining the operation of a stop button, then you can just connect it as a normally closed contact, so that we just understand its operation. But if you were to make use of it in the field, then we understand that the stop button will come as a closed contact already, and so we use a normally open contact within the software part. Okay? I want to believe that would make sense. Again, this would be clearly illustrated if you try this. And that's why I want to work on a demo. I have a software here that's going to help me come up maybe with a demo and demonstrate some of these things to you, so that we change that normally open contact into a normally closed contact and we see what happens, if it works or if it doesn't work. I think that seeing is believing. So maybe that's the way to go. I will figure out the best way to do that. Anyway, let me at least draw this diagram to do it later. Okay? Guys, just give me a minute. I'm receiving a call here from the chairman. Let me just receive that call, and then I continue. All right, sorry, gentlemen, ladies. Let me just draw this diagram for you to be able to maybe go through it. Then in the next class, because in the next class I wanted to go to counters, but I can explain the operation later, and then we continue. So maybe let me just put it here so that you go and for those who want to simulate it or for those who just want to understand it. So anyway, the conditions that are given here is that we have the start button, okay? We have the start button here, because the first one I told you is just a latching circuit. So we have this stop button, but it's activated. So this is stop. And we are putting it as a normally open because the stop button here is already in the normally closed position. This is already in the normally closed position. And then, of course, the condition that was indicated here was that before starting the pump, PS1 must be closed. So it means as it is, PS1 is open, but before the pump starts running, it must be closed. You can see PS1 is in the open position. Even in the diagram that I drew, it's in the open position. So for the pump to start, PS1 condition must be met. So we have PS1 here. And then, of course, you have your pump output. So this is your pump. Such that you want the start button pressed so that this is logic 1. Okay. You have the stop button, which is already active. Okay. And because the stop button is already in the normally closed position, if it is passing logic, that is, if it is activated, then you have a logic 1 there. And PS1 must be closed. So if the PS1 is closed, then this is logic 1 and the motor starts running. So that means if PS1 is open, then this is logic 0 and the motor can't run. So the reason why I have put it here, PS1, is because it is a condition for the motor to run. So if PS1 is open, that's a logic 0, the motor will not run. If the PS1 is closed, that's a logic 1 and therefore the motor can now run. Okay, that's why it's put there. So you have the start button, the stop button, and the PS1. But remember, this was a latching circuit. So because it is latching, we have to take the output and branch it out on the input. So this guy is the pump, okay? So that even if you release the start button, the pump should just continue working up until somebody presses the stop button, okay? So that essentially, I'm not sure whether it's complete, we'll see it, but essentially that should be the diagram for this, the first rung. The second rung, it says that the pump is just the condition here, where we are expecting PS2 and PS3 must be closed 5 seconds after the pump starts, all right? So, in fact, we can put this in the second rung, this condition, PS2 and PS3 must be closed 5 seconds after the pump starts. So therefore, we have to put a condition where we achieve a delay of 5 seconds. So the delay of 5 seconds, it means the pump needs to be running. So I can use the output there for the pump, so that if the pump is not running, there's no need of the delay. There's no need of the timer. But if the pump is running, then the timer is activated. So this is where you put your timer, the on delay timer, such that now the preset value here, I think, is 5 seconds. So this is your start, and then this is your done bit. So you have your done bit connected there. So that, of course, I told you that if you are to draw this specifically, you have your done bit and you have your enable bit. Enable, once the done bit reaches 1, then the output is enabled. That's basically what we are saying, okay? Then the output is enabled, okay? So now the second rung is simply to achieve a 5-second delay after the pump is on. So if this pump is off, meaning if you have a logic 0 there, then there's no need of even counting down. But if the pump is on, then we expect the timer to count 5 seconds. And then once those 5 seconds have elapsed, then this condition has to be met. This condition has to be met, that PS2 and PS3 must be closed 5 seconds after the pump starts. If either PS2 or PS3 opens, that is, if either of them is not closed, then the pump will shut off and it will remain off for another 20 seconds. So in that case, therefore, we have to say, in that case, we have to take the done bit, okay? We have to take, because we have to know that, let's say the pump was on, the condition is met. So the pump is on, and therefore the motor is activated. I mean, not the motor, the timer is activated, and therefore it is running. So the timer counts 5 seconds. After 5 seconds, it gives us a logic 1 on the done bit. So that logic 1 on the done bit is what we used for the conditions of PS2 and PS3, because we are told PS2 and PS3 should be off at this point. If they are not off, then the timer, remember, PS2 and PS3 must be closed 5 seconds after the pump starts. So in our design, we are simply checking after 5 seconds, is PS2 and PS3 closed? If not, then the pump goes off for 20 seconds. So that's what we need to design on the third rung. And so let me just draw it. We'll probably explain it in the next class because time is up. So now the done bit is what we need, the done bit for this timer. So we can call this maybe timer T1. So done bit for T1, okay, is what we use. And remember, the condition is if either PS2 or PS3 is not closed. So, and remember, closed, not open. So if either PS2 or PS3 is not closed, either means we have to connect them in parallel, because it means either one condition is enough to switch off the pump for 20 seconds. So if either PS1 or PS2 is not closed, okay, then you have your off delay timer here. So T off. I don't want us to be logged off. So T off, and then you have a preset value. Again, this is start. You have a preset value of 20 seconds there. And then this is connected. You have your enable and your done bit there. Okay. So the condition is if PS1 and PS2 after 5 seconds, because you know, after 5 seconds, we'll get a logic 1 here. So if this is a logic 1, then we need to check either the condition of PS1 or PS2. If they're not in the closed position, that is, if either one of them is not closed, then the motor would, and remember the reason why I'm putting them as a normally closed contact here is such that if either one of them is open, and remember, it means if it is open, it is passing logic, because this is a normally closed contact. If it is open, it is passing logic. If it is closed, then it is not passing logic. So if it is open, it is passing logic, and therefore the time it activates the timer. If either one of them is passing logic, then the timer for the off delay needs to be activated so that we wait 20 seconds before the timer, before the pump goes on again. So maybe because of time, I'll not be able to complete this, but we'll do it in the next class because I also have another class right now. So you can just indicate it, and then we will have to continue in the next class. All right. So I will be able to discuss it further in the next class before I proceed to the new topic of counters. So allow me to end it here until next week. Please just read through this. In fact, this is available. This question is available in the book, so you can also read the book. Maybe the explanation is not given, but you can try and understand the diagram. It's given in the book I gave you, Petruzella, and it is under timers. Timers are discussed in chapter 7, so you'll find it there, and you can try and understand it before we look at it further and conclude in the next class and start on the counters. All right. So thank you guys so much. I think I want to wish you a good rest of the weekend. Of the week, and then we meet next week to continue from where we have left.